Hey kiddos, happy week 20. Today we're starting out the semester by introducing our new unit, which is work, energy, and power. You'll notice a new module on Canvas for this unit, and today we're going to introduce the idea of work. Then we'll use the work energy theorem to discuss safety mechanisms in vehicles. Okay. So first let's define energy, and this is something that you probably discussed in patterns physics if you remember the egg bungee jump from way back when. We won't be doing that again this year, but we are going to be discussing energy. So energy, just so you're aware, is something that is what's called an overarching concept. It will be fair game on any test for the rest of your IB physics career. Okay. A lot of questions can be asked and problems can be solved through the lens of energy. So what is it? It's the ability of something to produce change in its environment. Okay. Sometimes I call it the ability to produce screams. Sometimes I like to give an analogy of a roller coaster that we'll look at later. Okay, energy is the ability to produce change. Let's actually brainstorm some types of energy first. What have you heard of with regards to energy, right? There's chemical, mechanical, kinetic, potential. There's like places that you get energy from, right? So there's wind, solar, nuclear, geothermal, right? Things along these lines. We will be looking mostly at mechanical energy. So things that types of energy that impact the way objects move. Okay, so kinetic and potential energy. We'll look at a type of potential energy called gravitational potential energy, and then we'll also look at elastic potential energy. So mechanical is an overarching descriptor of the types of energy that are present when an object is moving or has the potential to move. And that's what we're going to be talking about in this unit. Eventually, we'll talk about all of those other types of energy. Okay, so first off, let's kind of review kinetic energy and gravitational potential energy. All right, gravitational potential is easy, I think. Right, gravitational potential energy, you may have seen it abbreviated E for energy, just like all of our abbreviations for force started with a capital F. It's easy to abbreviate all types of energy with a capital E and then give it a little subscript. So E sub G would be gravitational potential energy. You might also see in some other resources gravitational potential energy abbreviated in an uncommon way. It's a 3-letter abbreviation, gravitational potential energy, or GPE. That's not 3 things multiplied together, it's a 3-letter abbreviation, which is uncommon, except for in this instance. So E sub G or GPE, you will need to be able, right, to recognize both of those abbreviations and smoothly switch from one to the other. Okay, so I have a bunch of books back here. I will grab them and be right back. All right, so let's take a look at gravitational potential energy. It's an energy that's not due to an object's motion, it's due to its potential for motion. Remember, our definition of energy right here is the ability of something to produce change in its environment. Okay. What change does gravitational potential energy produce? Well, I've got this physics study guide. It's very thin, pretty light. If I hold it up just a little bit above my desk, not very far, it's kind of light, it's not very high, I drop it, makes a little bit of a thud. What if I drop it up higher? It'll make a, whoa, way bigger thud, okay? So we know that height makes bigger thuds, okay? So more height makes bigger thuds. We know that the book, when I hold it up, we know that it has the potential to fall because of gravity. This G is the acceleration due to gravity. And then what if instead I was going to drop our IB physics textbook, right? If I dropped it from up high, what sort of thud would it make? Way bigger. I'm not going to do it because it would be alarming. But right, mass makes a difference, right? In how hard something falls, the volume of the thud that it would make once it falls, right? So the equation that is typically associated with calculating gravitational potential energy is mgh, mass times acceleration due to gravity times height. And all of those are in SI units. All right, what about kinetic energy? That can be abbreviated E sub K, or also commonly just KE for kinetic energy. And if you remember from patterns physics, kinetic energy, the ability to produce change due to motion, just like gravitational potential energy, it has to do with mass, and it has to do with how fast an object's moving, right? If you have played like a ball sport, like I played softball when I was in high school, you know that if a pitcher hits you with a faster ball, you will scream louder because an object that's moving faster has more oomph, right? It has more energy. It has more ability to produce screams out of you because you are alarmed and or injured, right? And actually, the mass doesn't matter as much as the speed does. So in this relationship, there's a squared, and that just applies to the speed, okay? And also because of calculus, if you've got a squared relationship, there's a 1/2 in front of the constant. Okay, just like we had in our motion equation, distance equals 1/2 acceleration times time squared, right? With kinetic energy, we have 1/2 mass times speed squared, right? Mechanical energy, it's important to note, is a scalar quantity, which means it has no direction. Energy has no direction. Yay, no vectors. Duh. Okay, so that's good. So you don't have to worry about that in this unit for about 5 minutes. Okay, we'll get to a vector quantity here in just a moment. Okay, let's check out units. So always using SI units when we're discussing energy. Mass would be in kilograms. Right? We don't include numbers when we're figuring units. Kilograms times speed is meters per second. Oops, meters per second. And if we square the meters per second, we get meters squared per second squared. Okay? What about gravitational potential energy, right? It's another energy. It should be the same units. Mass is in kilograms. acceleration due to gravity, acceleration is a meter per second squared, times height is in meters. So hey, kilograms meters squared per second squared. Okay, so that's the unit of energy. And just like newtons, we're a kilogram times a meter per second squared. This has an extra meter in it. So sometimes this can be abbreviated as a Newton meter, right? Because a Newton, again, is a kilogram mass times acceleration. A Newton with an extra meter, and this is known as a joule, named after James Joule, and we abbreviate it with a capital J because it's named after a human being. Okay. All right, so the unit is a joule for energy. Right. Also, an idea that is inextricably intertwined with mechanical energy is the idea of work. Okay, the idea of work. So here's something that's kind of funny. When is work being done? Like colloquially, you think like if you're doing work, you could be doing mental work, right? You could be doing your homework. You could be doing physical work. You could be cooking in the kitchen. You could be gardening. You could be doing vacuuming the living room, any number of those things. Like if you're being productive, that's considered work, right? In physics, there is a specific definition of work. Okay, so there are a couple examples that I usually give, right? If I look down at my tabletop here, okay, if I'm pushing on my desk, am I doing any work? Actually, I'm not. I'm pushing on my desk. If I kept doing this, I'm exerting effort. My muscles would be sore. I would get tired, right? But I'm not doing work. Okay, what if I took this big physics textbook and I held it out in front of me, right? Without any support, I'm just holding it out. Will my muscles get tired? Yes, I'll start sweating eventually, right? But I'm not really accomplishing anything. I'm holding it up, right? We might colloquially consider this work, but in physics, it's not considered work, right? On the other hand, if I go down to my tabletop here again, and I have my pen, if I push my pen across the table, I've just done work according to physics. And what's the difference? Is that when I push the pen across the table, the force that I applied was causing the object to displace itself. Okay. So in physics, work is equal to force is a force that causes displacement. Okay, what are the units of work? Work is abbreviated as W equals F times D. The units of work would be newtons, right, for force, and meters for distance. Hey, we just said a Newton meter was a joule. So the units of work are also joules. So what are you doing when you're doing work? You're applying, it's actually a net force. You're applying an unbalanced force which causes an object to move. And you're changing something's energy, right? If you're applying an unbalanced force, something's accelerating. And I put the net right here, but from here on out, if we see an F for force, we are talking about a net